This is a fossil, a bone, picked clean, drying in the open air, slowly going gray under the sun. And right now, the odds that it will still exist in 100 million years are almost exactly zero. Not low, almost zero. Of every creature that has ever lived on this planet, every fish, every insect, every animal that ever drew breath, the share that left behind a single fossil is a rounding error. Less than 0.1% of species are known from fossils at all. The rest vanished without a trace. No bone, no tooth, no print. Gone, as if they were never here. So the interesting question was never how a bone turns to stone. The interesting question is how anything survives a process that's designed at every step to erase it. Taphonomy, the science that studies exactly this, shows that fossilization isn't one event. It's a gauntlet. 4 stages lined up one after another, and each stage is actively trying to destroy what the stage before it let through. Clear the first, and the second is waiting. Clear the second, and the third closes in. Almost nothing makes it to the end. This is the story of the things that did. It starts with a death, but the death is the easy part. Everything dies. The gauntlet doesn't begin until the body hits the ground. The moment an animal stops moving, it becomes food. A carcass in the open is a feast that the whole ecosystem comes to claim. Big scavengers tear off the soft parts first, then smaller ones, then insects, then bacteria, working the body down to scattered bone. On an open plain, a large animal can be reduced to nothing recognizable within weeks. The bones get gnawed, dragged, cracked open for marrow, bleached, and broken apart until there's simply nothing left intact enough to become anything. This first stage is a filter, and it's merciless. Most remains never clear it. They're eaten and recycled back into the living world, which is exactly what's supposed to happen. So the question that decides everything isn't how the animal died, it's where the body came to rest. Die on dry open ground and the gauntlet ends almost immediately. But fall into the right place and the rules change. Sink to the bottom of a still lake, get swept down a river and dropped under a sandbar, drown in a flood and settle into the mud, tumble into a bog or a tar seep, or the airless deep of the sea. In those places, the scavengers can't easily reach the body, and the clock slows down. And then there's amber, fossilized tree resin that can seal an insect or a feather in an airtight tomb so completely that creatures tens of millions of years old emerge with their color and their bristles still intact. A pathway so different from everything else that taphonomy treats it almost as a separate science. This is why the fossil record is so badly lopsided. It's overwhelmingly a record of the water, marine animals, river creatures, things that lived and died in or near mud and silt. Those dominate because their bodies came to rest exactly where burial was waiting. A clam on a quiet seafloor has a real chance. A bird that dies on a mountain ridge has almost none. The land, where most of the drama of evolution actually happened, is the hardest place on Earth to leave a fossil behind. Stage 1 isn't about dying. It's about landing somewhere the planet can start burying you before the world finishes eating you. If it does, the body clears the first filter, and the second one is already working. Now the body starts to disappear from the inside out. Even sealed away from scavengers, the remains aren't safe, because the threat is no longer external. It's internal. The animal's own bacteria, the microbes that lived in its gut and its tissues in life, turn on it the moment it dies. Decomposition begins. And in this stage, almost everything soft is lost. Skin, muscle, organs, the eyes, the brain, the parts that made the creature look like itself, break down and dissolve. In most environments, they're gone within weeks. This is why the fossil record is, overwhelmingly, a record of hard parts only. Bone, teeth, shells. The tough, mineral-rich pieces that were already halfway to stone while the animal was still alive. That's the trick of stage 2. The survivors are the parts that were never fully fleshed to begin with. Bone is built from a calcium phosphate mineral called hydroxyapatite, wrapped around a scaffold of the protein collagen. Shells are calcium carbonate, and teeth, coated in enamel, the hardest tissue any animal makes, are the toughest of all, which is why isolated teeth are some of the most common vertebrate fossils on the planet. An animal might leave behind no skeleton at all and still leave its teeth. But what really controls this stage is oxygen. Oxygen feeds the bacteria of decay. Cut off the oxygen, and decomposition slows to a crawl. So the very best fossil sites on Earth are the ones starved of it. The deep, still bottom of a lake. The dead, oxygen-free layers at the bottom of a stagnant sea. In those suffocating environments, the bacteria can barely function, and astonishing things survive. The Burgess Shale, high in the Canadian Rockies, preserved the soft bodies of creatures more than 500 million years old, down to their guts and gills, because they were buried in fine mud with no oxygen to rot them. Soft tissue almost never fossilizes. In the right airless grave, it sometimes does. That's stage 2, a race between decay trying to consume the body and the next stage trying to lock it away before decay can finish. And in the rare cases that matter, burial gets there first. This is the stage that saves you. Sediment, mud, silt, fine sand, volcanic ash, particles settling out of water or drifting down from the air, layer upon layer, slowly covering the remains. Once a body is sealed inside sediment, the war is essentially over. No scavenger can dig down to it. Oxygen is shut out. Currents and tides can no longer scatter the pieces. For the first time in the whole story, the bone is genuinely protected. Speed is everything here. A skeleton, lightly dusted with silt, can still be uncovered and scattered, but a body buried fast and buried deep by a sudden flood, a collapsing dune, a fall of volcanic ash, gets locked down before anything can disturb it. This is why the most spectacular fossil sites on Earth are so often records of catastrophe. Paleontologists have a name for these places: Lagerstätten, a German word meaning roughly storage places, sites where the conditions aligned so perfectly that whole animals came through with extraordinary detail intact. The Messel pit in Germany, a Lagerstätte, preserved whole mammals with their fur and stomach contents, victims of a volcanic lake that smothered them. Solnhofen in Bavaria, another Lagerstätte, a still and salty lagoon, captured Archaeopteryx, feathers and all, in limestone so fine it reads like a photograph. The Brea Tar Pits in Los Angeles are a different kind of Lagerstätte entirely. Not water and silt, but sticky asphalt that swallowed Ice Age animals whole and kept them in near-perfect condition for tens of thousands of years. The fastest, gentlest, or most sudden burials make the finest fossils. Then time and weight go to work. More sediment piles on top, hundreds of feet of it, sometimes thousands. The weight presses the buried layers together, squeezing out water and packing the grains tight. Minerals seeping through the spaces cement those grains into a solid mass. Loose mud hardens into mudstone. Sand becomes sandstone. This transformation of sediment into solid rock is called diagenesis, and it happens slowly over millions of years as heat and pressure and mineral-rich groundwater do their work. The soft sediment around the body turns into solid sedimentary rock, and the remains are now sealed inside it, frozen at a precise depth in a precise layer in the crust of the earth. But here's the thing that surprises people. The remains are protected now. They're wrapped in stone. They're not stone yet. That bone is still bone. To truly become a fossil, it has to be transformed, atom by atom. And that's the final stage of the gauntlet, the strangest one of all. Buried deep in the rock, the bone is porous. Under a microscope, it's full of tiny channels and empty spaces. The gaps where blood vessels and living tissue used to be, now hollow. And through the buried rock, groundwater is always moving, slow, patient, and loaded with dissolved minerals it is picked up along the way. Silica, calcite, iron, pyrite. That mineral-rich water seeps into the bone, into every pore and channel and microscopic gap. And there, over thousands of years, the minerals crystallize. They settle out of the water and harden inside the empty spaces, filling them solid. This process is called permineralization, and it's why so many fossils preserve impossible detail. The mineral pours into the existing structure and sets, casting a perfect interior replica. The growth rings inside petrified wood, the microscopic canals running through a dinosaur bone, the chambers of an ancient shell, all of it copied, because the stone simply filled the shape that was already there. Sometimes the gauntlet goes one step further. In a process called replacement, the original material itself dissolves away, molecule by molecule, while new minerals take its place at the very same moment. The bone is gone. What's left is an exact mineral duplicate standing in for it. And the mineral doing the replacing changes everything about the result. Silica makes hard, glassy stone. Iron pyrite, fool's gold, turns ancient ammonites into objects that look cast in metal. And in a few rare places, like the opal fields of Lightning Ridge in Australia, the replacing mineral is opal itself, and the fossil comes out of the ground as a shimmering rainbow-colored gem. This is the stage that demands real time. A skeleton from last century isn't a fossil. By the common definition, remains have to be at least 10,000 years old to even qualify, and the famous ones are far, far older. Millions of years, tens of millions. By the time the process is complete, that original bone has spent longer as stone than its entire species ever spent alive. The transformation is finished. The shape remains. The structure remains. The animal is gone. And in its place sits a stone that remembers it exactly. 4 stages: cleared, death, decay, burial, mineralization. Each one a filter the one before had to pass. And the body made it through all 4, but it's buried a mile underground. And a fossil no one will ever see is, in a sense, still lost. For us to find it, the planet has to hand it back. Tectonic forces lift the buried layers over millions of years, pushing ancient seafloors up into mountainsides and dry plains. Then erosion takes over. Wind, rain, and rivers grinding away the rock above, stripping off the layers one at a time, until at last, the fossil reaches the surface and meets daylight for the first time in an unimaginable stretch of years. And here's the final cruelty of the gauntlet. The same erosion that reveals a fossil is also what destroys it. The moment it's exposed, it's on a clock. Frost cracks it, rain dissolves it, wind wears it down. A thing that survived 100 million years underground can crumble into gravel in a few seasons in the open. A fossil doesn't only have to survive death, decay, burial, and the slow turn to stone. It then has to be found by the right pair of eyes in the narrow window between the moment it surfaces and the moment it's lost again for good. Death, decay, burial, mineralization, and then the gauntlet of being discovered at all. The odds against any single creature running all of it are almost beyond counting, and yet they're in museums. They're in cliff faces and road cuts and the dry gravel of desert riverbeds. Every fossil you have ever seen ran the entire gauntlet and won. So the next time you stand in front of one, remember what you're actually looking at. Not a bone, a survivor, a body that became stone and then waited 100 million years for someone to come along and read it. That bone in the sun, with its odds of almost 0, this is what it looks like when the almost wins.